Hi, everybody. So this video, I want to start off with, again, we're in section 3.2. And I want to start off with a very fascinating thing, the derivative of the integral. It sounds like taking a humidifier and a dehumidifier, and they kind of cancel each other out, which is sort of what happens here. So a of x, I'm just looking over here, a of x is equal to the function, the function a of x, as it's a function of x now, is the integral from 0 to x, there's our x right there, of f of t dt. So this is not a function of t, it's a function of x, because it changes, because again, this definite integral is a number, and that number changes when I change the x. Anyway, that's the function a of x, and a prime of x, which is d dx, the derivative of this integral 0 to x of f of t dt, is f of x, not f of t, but f of x, that x, that limit of integration up on top. And so it kind of looks like you're canceling out, but let's just do a very simple, straightforward example. I'm gonna switch cameras and set this up. So I have d dx of this gnarly looking integral. Well, the answer, I don't have to figure anything out. The answer is just going to be the square root of x cubed plus 1. So I'm taking that x up there and just plugging that into the t, and pow, that's my whole answer. It's that simple. I wanted to show you another kind of problem, a very interesting type of problem. Let me just draw it out for you. So f prime of t is equal to f of t, which is, that's so it works. It's that's capital F, small f. So this curve is y equals f of t, small f of t. And capital F, as you know, is the area under the curve, blah, blah, blah. But basically, the derivative of capital F is small f. So where does capital F have a relative max? Where does it have a relative min? Well, the answer is actually very simple, because if you notice, regular F is positive over here. And then regular F becomes negative over here, which means when t equals 2, now, so when t equals 2, since small f goes from positive to negative, well, when small f is positive, that means that capital F is increasing for, between 0 and 2 for t less than 2. And then when small f becomes negative, capital F is decreasing. When t is greater than 2. Although it's not going to be forever. It's gonna change when we get to 4. But let's just leave this for now. I'm just looking at this small neighborhood of 2. Well, we know when a function starts out increasing, so if f starts increasing and then it goes and starts decreasing, it means that you have a max in the middle. So we have a relative max when t equals 2. And here I have on the flip side, when t equals 4, it's going from negative to positive. So when t is 4, so capital F is decreasing. When t is less than 4. And then it also, since small f, which is the derivative of capital F, since the derivative is increasing, since the derivative is positive, that means the function f is increasing. And once t passes 4. Well, if something is decreasing and then it starts increasing, it means we have a min. So the min is going to be when t equals 4. And that's a very very cool kind of problem. I like that. It's very, very meta, very philosophical. But it kind of reminds me, it's kind of the principles we had with curve sketching. This is sort of some of the same tricks that we use, not tricks, but insights that we use with curve sketching. That since this function that I've graphed here is really a derivative of capital F, So when the function is positive, that means capital F is increasing. Even though you see y is going down, but that doesn't matter. Y is going down, but it's a positive amount, which means capital F is increasing as long as the derivative, because y is actually the derivative of capital F. So it goes from increasing to decreasing power. Very nice problem. I want to do some more just basic integral problems just to just crunch out some numbers. And it's always good to have some practice. So let's do a few right now. So here we have a nice little problem. Is that all good? Yeah, that's right. Okay, so the integral from 1 to 5 of x cubed plus 1/5 x squared plus 3 over x dx. And what does that equal? So this is equal to, drumroll please. Well, first we take the antiderivative. So the antiderivative of x cubed is going to be x to the 4th over 4. The antiderivative here is going to, well, the antiderivative of x squared is x cubed over 3, but I have the 1/5. So this is actually going to be x cubed over 15, because it's, 15 is the 5 times the 3. And this one is actually going to be plus 3 ln x. That's evaluated between 1 and 5. And this is going to be 5 to the 4th over 4 plus 5 to the 3rd over 15 plus 3 ln 5 minus 1/4 plus 1/15 plus 3 ln 1. Now the ln 1 is equal to 0, so I can just get rid of that. Because ln of 1 always equals 0, no matter what the base is. So all I gotta do, and this here, ln 5, yeah, it's some ugly number, but it's just a number. So I'm just gonna stick this, somewhere in the end. All I gotta do is really just deal with these two fractions here. So it's 5 to the 4th minus 1 over 4. Plus 5 to the 3rd minus 1 over 15. 5 to the 3rd minus 1 over 15. And then, of course, plus 3 ln 5, plus 3 ln 5. And let's see, this is 5 to the 4th is 25. There's 625 minus 1 is 624. Oh, that's actually gonna come out to be a whole number. Plus, that's 125 minus 1 is 124. It won't be a whole number over 15. Plus 3 ln 5. 624 over 4. Let's just divide that. 4 into 624. So that's 4. That's 2, so it's 156. This equals 156 plus, well, how many times does 15 go into 120? So that's going to be 8 and 4. That's, let's see, 15 times 8 is 80 plus 4. Yeah, so that's 8 and 4/15 plus 3 ln 5. And finally, just to make it a little bit nicer, so it's going to be 156 plus 8 is 164. 164. 164 and 4/15 plus 3 ln 5, and that is the answer. And that's my answer, and I'm sticking to it. So there you go, 164 and 4/15 plus 3 ln 15. I want to show you an interesting problem that's in our textbook. So I'm just gonna show you this little problem from our textbook, and I'm gonna talk you through it. So let me switch cameras. Just take a second. So this is example 7 from our textbook. The graph on the right shows f prime of x, and that, of course, is the rate of change of f of x. We all know that. And we want to use this graph here of f prime to sketch a graph of plane f, and we want that graph to go through the origin. We want f of 0 to equal 0. So first thing I want to say is that this graph here is plane f. So plane F, if you notice, plane F is going it. So when, excuse me. So we're just reminding you that this is again, this stuff we saw in the previous chapter, that when F prime is positive, then plane F is increasing. If plane F is decreasing, F prime is negative. When F double prime is positive, that means that F regular prime, F single prime is increasing and the function is concave up. When F double prime is negative, then the function is concave down. And of course, F double prime, F single prime is decreasing. So here we have, so this function, this graph here is the F prime graph. It's not the F graph, it's the F prime graph. So here F prime is positive, which means regular F is going to be increasing over here. Here F prime is negative, which means regular F is going to be decreasing. And over here, regular F will be increasing again. Now, notice that over here, this whole way down, F prime is decreasing and decreasing until I get to that point right there. Since F prime is decreasing, that means that the function is going to be concave down. And then from this point on, F prime is, even though F prime is still negative, but it's increasing. And since F prime is increasing, the function is going to be concave up. And we're going to put all that information together, and we're going to graph this sucker. So the book, I didn't draw this out because the book is going to draw this out. And so when the so again, from 0 to 1, the function is increasing and it's concave down, like we were saying. Then it starts decreasing, but it's still concave down, and that's possible. And then it continues decreasing, but it becomes concave up, and then the function starts increasing, and it's concave up again, and it stays increasing and stays concave up. So this is increasing concave down. That's decreasing concave down. That's decreasing concave up. That's increasing concave up, and that's again increasing concave up. So you just got to put all these little sections together, and we want to getting. Now we also have the fact that f of 0 equals 0, so that's why otherwise I wouldn't know where to put this thing. But here we go. So it's increasing and concave down. It's decreasing and still concave down. This is a point of inflection when x equals 2, and it's decreasing and concave up, and now it's increasing and it's concave up. And that is beautiful. Oh, I think there's a little typo here. No, I'm sorry, no typo. Everything's fine. So that's the graph. Now I can't just. I'd love to show this to you in Desmos, but I can't because this is they never really told us what the function is. They just gave us this raw information. And now if we smooth it out, this is not so horribly bad. But if we smooth it out, the graph would look more like this, which is just, and this is just a smoother version of what we had up there. So that's our graph of f of x, and it's just a smoother version of what we have over here, but it has all the same things. It's increasing concave down, decreasing concave down,